Hello everyone, welcome to the tutorial for Chapter 6 and Chapter 7, or if you are using version 2 of the textbook, it's Chapter 7 and Chapter 8. In these two chapters, we will first talk about information criteria and then talk about the regression model with interaction terms. In future chapters, our models will become more and more complicated. Previously, we may use the ratio of R squared as a matrix to determine the performance of our model. However, we all know that R squared cannot prevent us from overfitting. As we have more and more predictors, R squared will definitely becomes higher. So we need some new metrics or new criteria to tell us how to balance between the number of predictors in our model and the performance of our model. These metrics are called information criteria. In the textbook, the author introduced the ideas of entropy, divergence, deviance, AIC, WAIC in very detail. So the contents I provided here are just some summary, so I highly recommend you to read the textbook and understand better. So let's jump to the interaction. It's chapter 7 for version 1 and chapter 8 for version 2. And in this chapter, we will talk about two kinds of interactions. The first kind is a categorical variable with a continuous variable, and the second type are continuous variables with continuous variable. For the categorical variable with a continuous variable interaction, we will use the RUGD dataset, and we want to know which factors have impact on the GDP of a country. And we will start to add some interaction terms in our model. Firstly, we have to do some preprocessing. So we first extract the countries with full GDP data without NA values, and then we rescale some variables. Firstly, we take the log on the GDP value to have log GDP, and then we standardize it by dividing log GDP with mean of log GDP to make the average of log GDP being 1, and downscale the distribution of GDP values. And then for the RUGD data, with the max scaling technique, so we divided original data by the maximum value. So now the standardized RUGD data will be a percentage of the maximum value. Our model will be like this. Well, our y will be log GDP, and it will be estimated by alpha plus beta times x. So again, we have to start from prior diagnosis. The alpha value should be close to the average log GDP value, which is 1, because we have scaled our data. And for the beta value, the most extreme case of the beta value should be the maximum log GDP minus the minimum log GDP, which is 0.6, and it should be either positive 0.6 or negative 0.6 for the most extreme beta value. Without this prior information, we may set a very flat prior. So for example, we may set our alpha value from a normal distribution with mean equal to 1 and standard deviation equal to 1, and the beta value will follow a standard normal distribution. However, with this prior information, we can set a more regularized prior. So the alpha value can be follow a normal distribution with mean equal to 1 and standard deviation equal to 0.1. And the beta value can follow a normal distribution with mean equal to 0 and standard deviation equal to 0.3. So you may wonder why 0.3, because the most extreme value of beta should be around positive 0.6 or negative 0.6. So a standard deviation of 0.3 will cover like around 80% of the least value. And here we can compare the effect of the flat prior and the regularized prior. So I plot the maximum log GDP value and minimum log GDP value with these two black lines. And the two blue lines are the most extreme slopes value. This is positive 0.6 and this is negative 0.6. And then we can use a for loop to loop over the 100 samples we draw from the flat prior distribution and regularize the prior distribution here and have our result. So you can see that if we use a flat prior, the prior distribution of our regression lines are most of the cases are very unreasonable with the constraint compared with the constraint. However, if we use a regularized prior, you can see that most of the regression lines we draw from the prior distributions are possible for our data. You can see that most of the lines are having slopes between these ranges, and and they have most of the value predicted by the regression line are within the maximum and minimum value of the log GDP value. The first model we will learn is the basic model, simple linear regression, and basically the codes are the same as previous examples, but here, before we need to compare the model using some information criteria, like calculating WAIC value, so we need to use the log-like. So here we would like to calculate the log likelihood value of each observation under the parameters we've estimated. So here we use a for loop to loop over the observations we have, and using the normal LPDF function, and the function here will calculate the log likelihood value of the y under the distribution, under a normal distribution constructed by these two parameters, and the predict mu value is what we calculated here. Basically, it's the alpha plus beta times rug. So you can think of this log likelihood value as how common or how plausible is this observation drawn from the distribution we've estimated. The second model is the different intercept model. So here we have one for Africa and one for non-Africa country. Again, I use the index coding here to simplify our model code. And the third model is the new model with different intercept and different slopes. So this is our first interaction model. Actually, the model with interaction in terms of continuous variable and categorical variables together is very similar to the different intercept model. So let's look at the stand code. Firstly, the data part is exactly the same. We also need to set how many levels are in our categorical variables, and to continue our y value and our x value and our categorical variable. And the parameters part, for now, in this case, we need different value for the intercept, and we also need different values for the slope. We set them to arrays of length L. In the model part, we still need to declare the vector mu and calculate the mu equals alpha plus beta times x value. But here we need to set the index coding for both the alpha value and the beta value. And then we can set our sampling statement and the prior distribution as what we did in previous example. In the generated quantities block, I just copy the code from model 7.2 and then replace the line of prediction mu with our new formula. And it's done. And then we can compare the posterior results of these three models. So the first simple linear regression model is very simple. We just extract the output and select the prediction mu and prediction y, calculate the confidence interval, prediction interval, and plot the result using geometric line and geometric ribbon. And you can see that the result is like this, and ruggedness cannot explain GDP in this very simple linear regression model. The second model is the one with different intercepts, and we didn't talk about how to plot the posterior of different intercept model, and we will talk about it here. And then in the second model, it's the different intercepts model. We didn't talk about how to plot the posterior for a model with different intercepts, and we will learn about it here. We can look at the result first. So for a model with two intercepts, we may want two regression lines on the same plot and with their own confidence interval, and observations of different intercepts should be set to different colors as well. So how can we draw a plot like this? So we can actually modify the plotting code from result 7.1. So firstly, I add the original data of GDP, ROC, and Africa in the result 7.2 data frame, and then here I changed the result 7.1 from 7.2, and in the ggplot function, I add one more aesthetic called field. So the field aesthetic will control the fielding color of all the geometric point, geometric line, geometric ribbon. So this field aesthetic set at ggplot function is like the parent attribute of this plot. So I want different field color for Africa and non-Africa countries. So I use the if-else function. So if the Africa value equal to 1, this function will return Africa. Otherwise, it will return else. So we change the GG title from model 7.1 to 7.2 and plot the result. You can see that this plot is very similar to our ideal status, but notice two things. Firstly, the prediction intervals are overlapping a lot, and then the points are all in black. And third thing, we don't want to have our function in our plots as well. So we can further modify the code here. And the first thing I do is to remove the line for prediction interval. We can have some sense of a prediction interval by seeing the confidence interval, so it's fine. And also the geometric point part here, we need to reassign the shape of the point because the default shape only have one color, black. So we need to set it to shape equal to 21, and we can get a result like this. You can see now our points have different colors, but the outer bound of the borders of the points are still there. So if you don't want them, and you can set the stroke variable equal to 0, and this will remove the border, and you can get the result. And the last thing we need to do is to change the if else function. So we can use the labs function and set the field part to country. And you can see that the ugly math function disappear and is replaced by the value we set here. And if you want to separate these two lines on two different plots, but you want them to show together, and you can use the function called facet wrap. In the facet wrap function, you can put a tilde and before the variable you want to separate. So if you want to separate Africa and non-Africa country, I set the facet wrap tilde Africa, and it will automatically separate Africa equal to 0 and set Africa equal to 1. And at the same time, keep the colors we've set. In model 7.3, actually the code here is exactly the same as the code in model 7.2 because the prediction mu and prediction y were calculated in the stand output, so we can get the results using the same code. And the plotting code here is exactly the same as what we did in the last example. So you can see that now the only difference is now we have two kind of slopes for Africa country and non-Africa country. And by setting different slopes, you can see actually ruggedness is an influential factor for GDP, but the effect on Africa country and non-Africa countries are different. At the end, if we want to use some metrics to compare the model performance of these three models, we can use the rethinking compare function. And once you have set the log-like value in your STEM model, the rethinking compare function can calculate the WAIC directly for you. And you can see the WAIC value for model 7.3 is the lowest. And this means that model 7.3 explains our observation the best compared with the other two models. And then we come to the second section of this chapter, interaction term with two continuous variables. So the dataset we use in this example is a tulip dataset, and we want to know what are the influential predictors for the tulip blossom. So for the tulip column, we use max scaling because we want to keep the 0 value. And for water and shade, we move them to the center because the original data will be like 1, 2, 3 value, and the same for shade. This means a different level of water and shades. And we want to make it more intuitive, so we use the means center scaling, so it will be -1, 0, and 1. And then we can start to write our model. So model 7.4 is the basic multiple regression model with two continuous variables, beta 1 water and beta 2 times shade. So the parameters here are very simple. And the model 7.5, the interaction model, is actually very simple. We just add one more parameter, beta 3, and let it be beta 3 times water times shade. And in the stand code, the only thing we need to change is this mu formula. So now we have alpha plus beta W times water and plus beta S times shadow, and third beta water shade times water and shadow. And notice that we use the dot star function here again. So recall that this is the pairwise multiplication function because water and shadow two vectors. So if we want to do, if we just type water times shadow, then we want to do a matrix multiplication. However, the dimension will not match. So we need to use the point star function to do a pairwise multiplication for two vectors. And if you want to use the pairwise multiplication function, you can use the for loop to loop over all the rows of our observations as well. And you can just type. And then we can plot the result to see the relationship between our y and x. So we will have two plots, and one for a blossom with water and one for a blossom with shadow. So let's plot the relationship between water and blossom first. So here is the code for just the code I copied from tutorial chapter 5, and if we just plot it, you can see the result is very strange because there is a weird gap here, and that's because we have two variables, water and shadow. So we would like to separate the relationship between water and blossom with a different level of shadow. So we can use again the facing graph function, and you can see the result now looks better. So we can see when shadow is -1, the relationship between water and blossom is like this, and this is shadow equal to 0, this is shadow equal to 1, and the slopes are the same because we only have one parameter control the slope between water and y, but the intercepts are different because intercept in this example is also impacted by shadow period. I guess some of you may feel terrible on these three values here because they are not showing any useful information. So I want to change this -1, 0, 1 value to something else. I add one more variable called shadow level, and I use the pass function to create the column. So by doing so, it will be like this. So I will have shadow level equal to -1 and 0 and something else. So this is more informative, and I can change the shadow variable here to shadow level. And you can see the three values here are now changed to shadow level equal to -1 and 0 and 1, which is more informative. The same thing can be done on the other way. So we can now add another variable called water level and change the water to shadow here and shadow to water here. And the result is like this, with different levels of water, and the intercept for the relationship between shadow and blossom are also different. And the plotting code for model 7.5 is exactly the same as the code for model 7.4. But you can see now we have different slopes at different level of shadow, or different slope or at different level of water. That's because we have the additional beta 3, which will alter the slope coefficient with when water and shadow are different. So how should we explain the varying slopes model? So tulips need both water and light to produce blossom. At low light levels, like shadow level equals 1, water can't have much of effects because the tulip don't have enough light to produce blossom. At higher light levels, water can matter more because now tulips have enough light to produce blossom. And when light level is very high, light is no longer limiting the blossom, and so water can have a much more dramatic impact on the outcome. And at the end, we can again use the rethinking compare function to compare model 7.4 and model 7.5, and you can see that model 7.5 has a much smaller WAIC value compared with model 7.4. So it's definitely a better model, and it's more reasonable. And we use some when we apply some realistic knowledge. And this is the end of the chapter, and hope to see you soon next time.